if we wanted to build an AI assistant that could help us with everyday tasks, like it could be in our kitchen with us, helping us make dinner, or it could do complex tasks like helping manage our calendar, what abilities are currently missing from state-of-the-art AI that we would need to improve? So I think you would need to improve the ability to coordinate with other agents in shared spaces and learn from interacting with humans. But I think we actually need fundamental improvements in the state-of-the-art AI abilities to just learn complex tasks and generalize to new environments. So, if we train our agent in one kitchen, it needs to be able to work in everyone's kitchen. So I'm going to make the claim that actually social learning can help address all of these desiderata. So it might be obvious to you why social learning could help with social tasks like coordination and interacting with humans. But I actually think it can be helpful for fundamental tasks, just like learning and generalization. And to think about why, let me first define what I mean by social learning. So I just mean learning from other intelligent agents that are in your environment. So you can think of other agents as a valuable source of information that you might be able to benefit from. If you're an autonomous car driving on the road, other agents are doing things that might indicate to you what is the correct behavior. And social learning is an incredibly powerful learning mechanism that's used ubiquitously by both humans and animals. So, and it can help with things like generalization. Even this little 1-inch fish can, when it's dumped into a new environment, locate safe sources of food by taking cues from where other fish are gathering. And birds, in the UK, they have this example of birds learning to open milk top bottles. And it's not that each bird independently discovered this behavior. They're able to observe other birds and learn from what they're doing. And then, of course, many authors have argued humans are the animal that have taken these abilities to the next level. So the key differentiator between us and other species is actually our social learning abilities. And it's those that have led to our impressive cognitive, cultural, and technological development. So social learning can accelerate learning. Individual learning can be error-prone, expensive, and time-consuming, but social learning enables you to stand on the shoulders of giants and quickly acquire complex behaviors. So what I'm asking in my research is, how can we study social learning for AI agents? And specifically, I look at kind of two situations. You're in a multi-agent situation where you have other AI agents that you can potentially learn from, or you're actually interacting with humans, and how do you learn from those humans? So my work kind of spans the gamut from the more human AI side, like detecting and learning from human social cues, coordinating with other agents, to the more multi-agent side. So studying social learning in multi-agent systems and how to design multi-agent systems so that they give rise to the emergence of complex behavior. And it's those two last points that I'm going to focus on for today. And part of the reason for that is that I think this work most illustrates this claim I'm making that might be a little controversial, that social learning can actually help with these fundamental abilities like learning and generalization. So for today, I'll talk about these two topics, and let's dive into the emergent complexity topic first. All right, so let's say that I want to train a robot in simulation to be able to walk upstairs. So I really care about this property of generalization. I need my robot to be able to effectively deal with situations that it might not have exactly encountered during training, right? And so let's say I want to do this, and I build a simulator of stairs that has parameters like the height, the width, and the texture of the stairs. In order to make sure my robot can generalize to the real world, I might do a really common approach called domain randomization. And what that does is say, I'm going to randomize all those parameters in my simulator. So each episode, I'm training this agent, I'm going to randomly sample a new height, width, texture of stairs. I'm going to train on that distribution. And I'm going to hope that, whatever the real world looks like, it's going to be contained within that distribution of things that I trained on, such that I can transfer to it effectively. And let's say this actually works for me. And I managed to, in simulation, train a robot that can walk up these real world stairs as pictured here. And I say, fantastic. I'm going to start a company. I'm going to, make autonomous household robots that walk up everyone's stairs. I'm going to make $1 billion. It's going to be fantastic. And then I actually try to deploy my robot to the real world, and I run into some issues. So the issue with the real world is it's very diverse, and it's unlikely that I thought to code, this particular set of diagonal stairs into my simulator. The idea that everything you might encounter in the world is just different parameterizations of a simple simulator, to me, is untenable. So I think what we might actually want, is not only a set of complex training environments that prepare us for unknown real world challenges that our agent might encounter. But we don't have to anticipate and program all of those scenarios ourselves by hand, because that's just going to be brittle, error prone. I'm going to miss stuff. So maybe that's not the best approach. So if I'm thinking about making my agent more robust, there's this thing called adversarial robustness. What if I could learn an adversary policy to build environments such that they minimize the performance of my agent, such that they challenge my agent to do better? But as you might see in this video, can anyone spot what's gone wrong with that approach here? So the blue agent is trying to get to that green goal, and the adversary has placed these blocks. Anything wrong with the way it's placed the blocks? Yeah, I mean, actually, the adversary succeeded in its job. It's basically completely blocked off the goal, right? There's no path for the agent to actually reach the goal. So it succeeded in minimizing the performance of the agent, but the agent has no ability to solve the task or to learn from this environment. So essentially, we're just wasting computation. This isn't doing us any good, right? And so what the people in the literature have done to use this adversarial approach is say, okay, oh, do I have a question okay, never mind. So what people have done is they've said, okay, we're going to have an adversary, for example, applying forces to an agent that's trying to solve this inverted pendulum task, but we're going to set some constraints. So the adversary is not allowed to apply more than X force. And the problem with this is, like, for each new domain where you want to train an agent, you have to hand tune those constraints. And again, we're just doing like all this hand tuning, and it's kind of brittle. So I asked myself, is there a more elegant way to ensure that the adversary cannot create impossible environments? And ideally, we want those environments to be tailored to the current skill level of the agent that we're trying to train. So we kind of want a curriculum of increasingly hard environments. Now, of course, there's this hypothesis that multi-agent systems can give rise to the emergence of an automatic curriculum, because as one agent is adapting to the other agent then in turn adapts, forcing the problem to be harder for the first agent. So you get this emergence of complexity. So what if we make this whole setup a little bit more multi-agent? So that's actually the idea behind this algorithm I'm going to describe today. Instead of having this adversary generate an environment for a single player agent to play, we're going to take that agent and rename it a protagonist and introduce the second antagonist agent. And we're going to constrain the adversary using the performance of this antagonist. So you can think of the antagonist as allied with the adversary. And what the adversary is trying to do is maximize the regret between these two agents. So what it does is it says, I have to construct an environment where, the antagonist can do well. So the environment must, in principle, be possible to solve. But I'm still going to exploit the weaknesses of the protagonist and make it more robust. So I'm still going to find the environments where the protagonist is not able to solve them. So we call this approach protagonist, antagonist, induced regret, environment design, which is obviously a huge mouthful, but we think paired accurately describes how we're using this pair of agents. And the reason I'm referring to it as the regret is what we can show is that if you assume the adversary and the antagonist are allied, and that this game reaches a Nash equilibrium, then it's basically a two-player zero-sum game. So if it reaches a Nash equilibrium, we can show that the protagonist will be playing the minimax regret policy, meaning it's minimizing its worst-case difference from the optimal policy across all of the environments. And not only does that make it more robust, so it tends to succeed in an environment if it's possible to succeed, but this also gives rise to a nice curriculum. Which we can see in the generated environments as well. So what we see here is domain randomization, which is this common approach that I mentioned, generates unstructured environments that are not tailored to the skill level of the agent. As you saw, a minimax adversary can make impossible environments, but paired is like our Goldilocks. It's generating these structured yet challenging environments. And we see this curriculum emerging. So what we're looking at here is let's look at figure C. That's the shortest path length in the maze between the start state and the goal state, but it'll be 0 if the maze is impossible. So again, you see this minimax based approach, the red line, driving that metric towards 0. But in contrast, the paired adversary is generating increasingly complex environments And then on the right, you see that the agents are responding by solving increasingly complex environment. And what's cool about this is at no point where the environment generator or the agent ever trained on path length as a goal. This is just something that emerges out of the training procedure. And I think the most promising piece of the results are these ones. So what we're doing here is we're transferring agents trained with each of these training protocols, zero shot, meaning they can't train on the new environment, to a series of challenging human-designed test tasks. And what we see is that as the complexity of the test task increases, so does the performance gap between paired and these baseline techniques. And for the extremely complex tasks like the maze environment, only paired is showing any evidence of being able to solve it some of the time. So these results were actually promising enough that we ended up collaborating with a Google product team to try to deploy an agent based on paired into Google Assistant. So basically, Google would like an agent that, you could say, okay, Google, go buy me a keyboard, or okay, Google, book me a flight to Los Angeles leaving on Friday. And it would go navigate, for example, the Delta website, put in your information, complete that task for you. But not only is this really hard because websites are very complicated and navigating them is challenging, but you need really good generalization to be able to do this, right? If Delta updates their website, your agent can't cope with that shift in the distribution, it's going to break, and that's not good. So what the team was initially doing was, hand programming a curriculum of easy, medium, hard, and harder websites. And what you see is that actually the agent is not able to solve the hardest websites because it is a challenging task. So we said, okay, can we do better if we do something based on paired? And so we actually parameterized this web environment such that an adversary could construct web navigation tasks out of elements and multiple pages. And what we see is that a curriculum did emerge. So early in training, the adversary is constructing web navigation tasks with very few elements per page. So it's very clear on each page what the task of the agent should be. Late in training, it dumps all of the elements together onto a single page, making the task much more challenging. And then we tested our agent on not only standard web navigation benchmarks, which hopefully I'm not going to get in trouble for that given the previous talk on benchmarks, but we also design a new benchmark to make things a little bit harder. And then we actually test our agents on real websites. So what we saw is that on the benchmarks, we were 4 times more successful than the state-of-the-art or SOTA prior work. Reaching more than 95% task success across all difficulty levels. And we actually test our agents on real websites, so hopefully grounding back to the task we care about. And we saw that for the initial results on the simpler tasks, like logging into a website, we're getting very promising high success rates. So we're still working on this in conjunction with the product team, and hopefully we'll make that into Assistant. So in conclusion, what I want to show with this work is that you can think of multi-agent training, and especially this emergent complexity angle, as an effective tool for improving the learning and generalization, even for a single agent, even in a single agent task. And of course, we think paired is a good idea because this approach incentivizes the adversary to create feasible yet challenging environments that make the protagonist more robust. And this regret minimization lends itself nicely to not only robustness, but generating this automatic curriculum. All right. So I'm going to jump to the second part of the talk, and this is about social learning. So in a multi-agent system. So I said, okay, social learning enables you to stand on the shoulders of giants. But wait a second, doesn't imitation learning do that as well? So imitation learning is just saying, let's have a data set of expert trajectories and just use supervised learning to imitate that data set. So if I can predict what the expert would do, I can just do that as well. Just copy the expert. So that would allow me to rapidly acquire behaviors in the same way. But why not just do this? Well, one reason is that in not every scenario do you have access to a specially curated data set of expert trajectories, right? So you may not be able to collect that much human data, or it's not clear how the state of the human maps to the state of the robot in order to be able to imitate it. Those problems can probably be addressed, but with enough money or clever enough algorithm. But I think the more pressing issue is that, in imitation learning, what you're doing is you're copying the data exactly. So if your expert is not good, you can't improve upon the expert. You're only going to be as good as your expert data. And what you're seeing in this figure here is imitation learning methods in the case of inexpert data compared to reinforcement learning methods, and they just can't do as well. They can't outperform the expert that they're imitating. And then the third and maybe most pressing issue is that imitation learning is brittle. So the policies are really bad at generalizing to things that they haven't seen the expert doing. And I'll establish that later with some results. So in contrast, I'm interested in this question of using social learning in multi-agent systems to learn from experts. And so how is this different? It works in more naturalistic settings. So you should think of this as basically the autonomous driving setting. So you're in a situation where there are other agents in the environment where you're trying to do a task, but they're not motivated to teach you. So the other drivers aren't trying to train you how to drive. They're just trying to get to their destination. And they may or may not have relevant expertise. So there are drivers on the road that you probably shouldn't be imitating because they're bad drivers, right? So we want to think about learning who and when to learn from. So you don't have to copy the other agents exactly, but you can learn how to acquire information from the other agents. And what's cool about this is it can actually help you generalize or adapt to new environments. So for example, there's some interesting work out of Antagonist's work group at Berkeley, which shows that, if an autonomous car is very uncertain about what it should do, that's a great time to be copying what other drivers on the road are doing. So I think this is quite compelling. And we wanted to study how good are vanilla RL agents at actually learning from expert agents in their environment. So we created a multi-agent environment that had partial observability, and we put some expert agents in that were constantly demonstrating what you need to do to get high reward in that environment. And we put some novice agents in the environment. They have no privileged access to the expert's states or actions. So they're just in the same environment as another agent that's constantly showing them what to do, constantly demonstrating what to do. Interestingly, the agents that were trained in the environment with the experts, the social agents in purple, performed equally poorly to agents that were trained alone from the beginning. And neither of them ever reached expert level performance. So in spite of the fact that the experts are constantly demonstrating the correct behavior, the RL agent gets no benefit from that whatsoever. It just absolutely does not learn from that. So we still see that RL is like much dumber than this little 1-inch fish. We were able to add a pretty simple modification that helps address this issue. So instead of having your standard RL agent that's just learning what action is valuable to take and what gets high reward, we also added some layers to our network that asked it to be able to predict the next state given the current state. And because the expert is visible in its observation, the agent actually has to implicitly model what the expert is doing. And so now it's actually getting some signal, learning from what it's seeing the expert do. And this was enough to have our agents reach about equal performance to imitation learning methods, even though they had no privileged access to other agents. So maybe this is cool because you could say, oh, I can learn from other cars that are on the road without collecting data sets of what they're doing. Or I can address this issue where if a human is showing me a demonstration, I don't have to have the same state as the human as a robot. I can still learn from it. But you might also say, look, in many problems, I could collect this data set. Like, didn't you just do a much harder thing to be able to reach the same performance as imitation learning? Like, why is this cool? I think that's best answered by this slide. What we're looking at here is the generalization, once again, zero shot, of agents that were trained in a particular training environment with a set of experts, that was in orange, and how will they perform when they're transferred to a new environment. And what you see is the social learners in purple consistently outperform both the original RL experts that they learned from in their training environment and the imitation learners, which are shown in green. And this is where I'm saying imitation learning generalizes very poorly. It's very brittle. So we see evidence that, what's going on here is the social learners have learned how to acquire information from experts. So when they're deployed to a new environment with a new set of experts, they can leverage those skills to figure out what to do in the new environment. So this is potentially a promising path towards generalization. One of the coolest results that I got excited about was what we're looking at here is the performance of social learners when they're placed in an environment, in the same environment by themselves. So we're calling this like a solo environment. And what you see is that if we look at this orange curve here, the agents, as they initially start to use social learning to learn from the experts, they start to acquire a skill that they're able to use when they're alone in the environment. And so that's cool. But if you continue training with social learning, you see that that actually decays. The agents become overfit to depending on experts showing them what to do. You can correct this with a very simple modification. You just train those social learners in a mix of episodes where they're in an environment with experts and in an environment alone. And then we see that they're able to actually perform much better in the solo environment than agents that were trained alone from the beginning. So what you see is that what this means is they're actually acquiring behaviors from training with experts that they can take back and use on their own in the solo environment. So this is concrete evidence that the social learning is helping them acquire behaviors that they wouldn't be able to otherwise. All right, so this is pretty cool. And we see that social learning does help with these tasks of generalizing to new environments and learning complex behavior, but it's not the most sophisticated way to do social learning. So for the last few minutes of the talk, I'd like to dive into a little bit more math to show you kind of a more cool technique for doing social learning. And I realize it's going to get a bit mathy, but it's like 3 slides. You can make it almost the end of the day. So please bear with me. All right. So in reinforcement learning, a key quantity we care about is the total expected future reward that we're going to get if we action now from this state and continue on following our policy. So we want to estimate what's going to happen in the future, what's going to pay off in the long term. And we often refer to this with the Q value. So the Q value says, what's the total reward I'm going to get in the future, starting in this state S and taking this action A. And in this case, we're going to model that Q with this thing called successor features. So successor features breaks down that Q value into 2 components. The first is this psi. Now, psi is doing all the heavy lifting of estimating the future, which is the really hard thing that RL is doing. But it's going to break this out, not in terms of reward, but in terms of the future accumulated state features. So I'm going to care about certain things that are going on with the state, and I'm going to accumulate them into the future over time. So to make this more concrete, let's say that I was a little agent in a foraging environment, and I just need to pick up apples and bananas. My psi might track, okay, this policy is going to pick up 15 bananas and 2 apples into the future. And why is it useful to break these state features apart from this W? W is a preference vector, and it's just going to weight these features given certain weights that enabled me to compute my total expected future reward. So let's say my preference vector in this case is just, I like getting bananas and I don't like getting apples. When I combine this with my psi, I can then compute my future reward. Now, why is this useful to do? Let's say at test time, forget it. I don't want to pick up bananas anymore. I want to pick up apples at test time. Instead of having to relearn a whole policy that estimates everything about the future, all I have to do is swap out the W. And I can accurately compute the Q value of taking different actions if my goal has now changed. So this is a way of improving generalization and reinforcement learning. We decided we could use this in a really beneficial way in multi-agent reinforcement learning. So let's say we model ourselves, the ego agent, and the other agents in our driving environment, for example, using successor features. What that enables me to do is say, okay, I'm the ego agent, I'm modeling everyone else. I don't actually care about their preferences. I only care about my own preferences. So if I were to combine the other agent's expected state features with my preferences, I can then calculate how much reward I would get under my preferences by following the other agent's policy. So I can say, if I were to act like agent 2, would I get more reward than just acting like myself? And I can actually take the maximum over that to say, which agent should I act like in order to maximize my own reward? So effectively, the better I'm able to model other agents, the more I can optimize my own reward. But there's a slight problem with this. How can I guarantee that the other agent's psi that they're learning is compatible with my W? Like, what's the guarantee that agent 2 is even tracking how many bananas it's eating, for example? So I'm going to quickly dive into this. This depends on looking a little bit more at this successor features equation. So you might see that psi is policy specific. It's going into the future. It's detecting, how many bananas will I pick up according to my policy? That depends on my policy because, will I go towards a banana or not? That's policy specific. But this phi, the features that we're actually counting, can be agent agnostic. So phi might just say on every time step, did you pick up a banana? It doesn't depend on what agent you are. It's just a general feature representation. So the big insight in this work is we can share that phi across all of the agents. And what that means is that, if we're building each agent's psi out of the same phi, any signal we get about any of the agents, including ourselves, can help us refine that phi. So we get a lot of data about how to learn that phi. And data from one agent then helps learning the policy of the other agent. We learn the phi with this temporal difference loss, and we can learn each agent's psi, building upon it with basically a supervised behavior cloning or imitation loss. But what's even cooler is, the ego agent gets to observe rewards in the environment. So it's actually collecting rewards, unlike we can't see what the rewards of the other agents are getting. But that actually allows us to even further refine our phi and therefore refine our modeling of other agents. So to zoom out for a second, basically we create this feedback loop where the better I model other agents, the more that helps me take better actions and get higher rewards because I can essentially borrow from their policies if it's relevant. And then the more I interact with the environment, the more rewards I get that helps me refine my feature representation and improves my modeling of others. So we did a bunch of experiments with this. And what we see is that if in the case where all the other agents are doing the exact task that I need to do, I might as well just do imitation learning because that's very effective. They're just doing exactly what I need to do. And our method performs about as well as imitation learning. In the case where the other agents are all doing very irrelevant tasks, like parking in the middle of the highway, imitation learning fails epically because that's very bad behavior. But RL succeeds, and we do about as well as the RL methods. But in the case where the more realistic real world case where there's a bunch of other agents, some of them are doing things that are relevant and some of them aren't, our method actually outperforms all of these other techniques. And the cool part is that not only does it allow us to improve RL and maximizing reward, but it actually enables us to more effectively predict the actions of other agents than these imitation learning methods, especially under distribution shifts. We can use this as an effective inverse RL technique, so we can predict what rewards the other agents are optimizing. And we can use this to improve generalization. So basically, at test time, even if I've never once picked up a banana, but if I've seen you picking up a banana, I can do that task in one shot. Whereas an imitation learning method would take like 100 episodes to be able to adapt to that new task. So we're getting closer to this fish. All right, so in conclusion, we think of social learning as a powerful mechanism that can help you rapidly adapt to new environments and learn complex behavior, as well as these other social techniques. So thanks.